A lot of people go, well, if you have a planet here and you got something up here, well, why does it appear like it's at zero gravity in the movies or in some sort of video you see? Why doesn't it just come flying back towards the Earth? Because there's only the force of gravity acting on it. And the answer is this. In order to get out here, you got to be moving at a very high speed. You take a rocket ship out there, you fly out there, and then what ends up happening is you start to develop a circular path. And this force of gravity here is not strong enough to bring you any closer. It's only strong enough to redirect your motion so that you have a circular path. So we can model this as a circular motion problem. We have a satellite here that's orbiting around the Earth. This is orbiting at a radius r from the center of the Earth. So this actually is a pretty easy problem to model here. We do it as a circular motion problem. We say sigma f equals mv squared over r, and our only force is our force of gravity. Now keep in mind, this is our big mass, this is our satellite mass, little m. So we're going to say big M, little m here. We go mv squared over r equals g, little m, big M, over that radius squared. So you see the radius appearing in both sides of the expression there. And it turns out that the satellite mass doesn't matter here. One of those radii cancel out. So we get v squared equals g, big M over r. Square root both sides, you get this expression here. And this is a solution to our problem. This is what we call satellite speed. If your satellite's traveling at a certain speed, it can orbit at this radius. And essentially, you're going to find that, if you're looking at any sort of satellite, your satellites that might be over here, based on the fact that they're a small value of r, you actually get a large value of v, and they're going around pretty quickly. Whereas the satellites out here, they move relatively slow relative to something on the inside. So your greatest speed is going to be closer to the planet. Now, one thing that you have to realize is that a lot of our satellites that we like to have, we like them to be over the same point on the Earth at any given time. So if this is New Jersey and we want a satellite over New Jersey, the satellite speed has to pretty much match the rotation of the Earth the entire time. It's what we call a geosynchronous orbit. So in order for that to happen, you could also look at v and say, well, v is equal to 2 pi r over t. And if you set t to the equivalent of 24 hours, which would be 1,440 times 16, looks like 86,400 seconds. If it has a period of 86,400 seconds, basically what you could do is you could put that expression into there, into v, and then what you would get is that 2 pi r over t equals radical gm over r. And you can relate r to period, and if you put in 24 hours, you figure out exactly where you would have to have a geosynchronous orbit, which is all along a single line. So all those geosynchronous satellites we have are all along a single line around the planet Earth.